Good morning, everyone, and welcome to our session. I'm Eunju from Samsung Research, and today I'm so excited to talk about memory-efficient large language model inference on devices with NNTrainer. All right, so let's get started. Probably, for many of you, this may be the first time hearing about NNTrainer. So let's start with a quick introduction. NNTrainer is an open source framework designed to bring neural network training right onto the device. So why is this powerful? Because it enables truly personalized AI experiences across a huge range of devices, from your smartphone to your home appliances. Currently, NNTrainer is part of the NNStreamer organization, which is under the Linux Foundation's AI and Data project. And right now, it's actually under review to become an independent project. So today, we have two speakers lined up. First up is me. I'm Eunju, a staff engineer at Samsung Research. And as a committer of NNTrainer, I'm going to show you various use cases of memory-efficient large language model inference with NNTrainer.
Hello, I'm Donghak, software engineer at Samsung Research, contributing to NNTrainer since 2022. Today, I will explain how NNTrainer optimizes memory usage.
Thank you. So today, we are going to explore a key topic, memory-efficient large language model inference on devices with NNTrainer. So to set the stage, we will cover three keywords. First, we will discuss the importance and challenges of on-device large language models. So we will look at why bringing large language models to devices matters and the technical challenges we need to overcome. And second, we will move into NNTrainer's core features. You will see how NNTrainer is uniquely designed to tackle those memory challenges. And finally, today's highlight, including our demonstration, we will show you exactly how you can run super large language models memory efficiently on small devices. Then by the end of the session, you will clearly see how we bring the power of large language models directly to the devices with NNTrainer. So let's get started by looking at the first topic. Nowadays, we are seeing a wide variety of services leveraging large language models. But as you know, most of these services run in the cloud. But in contrast, the on-device execution we are focusing on today can offer several compelling advantages. We can highlight several main points here. First, it is privacy conscious. Since your data stays locally, so you never need to send it outside, which is very safe. Second, it can run in offline manner. The models can run anywhere and anytime. Third, customized user experience. Direct access to local user data allows us to deliver much more personalized AI services. Also, from the service provider's point of view, for example, application developers, running LLM locally saves significant costs compared to running it on the cloud. While those advantages are clear, running large language models on edge devices definitely come with significant challenges. These are three biggest issues we often face. First, limited computation power. Unlike the cloud, devices lack powerful GPUs with abundant memory, so they don't have good processing power. Also, there is strict power constraints, so these devices often run on batteries, which means they operate under strict power limits. Finally, and most of all, memory is the biggest bottleneck. So the limited available memory is the key barrier to delivering effective Gen AI services on the device. So let's take a closer look at the memory challenges. If you look at these two graphs, two things stand out. First, super large language models keep being released, And critically, those larger models are generally more accurate. But this brings us back to our reality. For the on-device environment, it is incredibly difficult to run even a model with less than 10 billion parameters, simply because of memory limitations. So let me give you an idea of the scale. So if a model uses full 32-bit precision, then you can roughly calculate its size by multiplying the parameter count by 4. So that quickly becomes enormous. So here is the central challenge. What we really want to do is to run a more accurate model, like 30 billion parameter model you see in this region, directly on the device. So here, this is the ultimate goal that NNTrainer helps us achieve. So let me explain it more with actual numbers. So first, we should understand that large language model inference requires memory for both runtime tensors and model weights. But let me focus on the weight size in this slide, because the weights consumed by far the most memory. So I'm going to compare two specific models. First one is 4 billion parameter model and larger 30 billion parameter model, since full precision models of them are simply too large for devices, so we usually use quantized models. For example, I've prepared the case using 4-bit quantization, which is what you see here in the second row of this table. So what do the numbers look like? For the quantized 4-bit model, as you can see, it needs 2.2 gigabytes just for its weight. And this might seem manageable for on-device use. However, the 30 billion model requires over 16 gigabytes for its weight alone. So when we think of a typical mobile phone's total RAM is around 12 gigabytes, then running that 30 billion model on device seems impossible. And remember, these tables show weight size only. So to actually run these models, we need even more memory for activations and KV caches as well. However, fortunately, we have NNTrainer. And NNTrainer can do this. So this is exactly where NNTrainer comes in. So if you see these videos, NNTrainer provides a memory-efficient framework that actually enables you to run even 30 billion and 20 billion parameters model right on your device. So these two videos show an example of running open model with 30 billion and 20 billion parameters models on Galaxy S25 Plus. So how do we overcome this physical memory limit? So today, we will explore the key technologies of NNTrainer that enable 30 billion large language model to run on device, with special focus on NNTrainer's memory-efficient solution. Before jumping to the LLM inference topic, let's first see how NNTrainer supports these crucial memory-saving features.
Now, I will explain what kinds of framework NNTrainer is. As Eunju mentioned earlier, we are part of Linux Foundation AI data project. NNTrainer is a framework that enables memory-efficient training and inference on device. NNTrainer was built from scratch, especially to handle the demand of training process. This is a key point because training typically requires at least 4 times more memory than inference. And our project is fully open source project, so developers can use it any way they need it. NNTrainer also supports a wide range of mobile device environments. It can run on operating systems such as Tizen, Android, Ubuntu, Windows, and it works with chipset manufactured by Samsung, Intel, Qualcomm, and NVIDIA. In addition to support many data types and shape, NNTrainer lets you choose the precision and compute engine for each layer individually. From this feature, developers can learn model with heterogeneous computing that maximize the use of device resources. So, NNTrainer is a framework designed to easier development of AI model targeting edge device. We aim to provide an optimized model serving experience in memory-constrained environment without requiring developments to consider hardware specifics. Not only in mobile environment, but also in low-performance edge device like home appliance. We implement many features and algorithms in NNTrainer. Today, I will explain two key concepts in NNTrainer. First, optimize tensor scheduling, graph-level execution order computation. Second is flash storage utilization. These two features make able to achieve a dramatic lower memory footprint compared with other frameworks. First, I will explain about tensor scheduling. Focus on the memory usage of a single layer while training. We reduce the overall memory usage by recognizing that the amount of memory required varies at each stage of training. Other frameworks don't account for on-device constraints, so they allocate all required memory upfront and keep it for the entire training process. NNTrainer, on the other hand, only allocate the memory that's necessary for each individual step. At forwarding step, as you can see, other frameworks allocate all memory for entire process, but NNTrainer allocate exactly they needed. At calculate gradient step, we need input and gradient and derivative of output and weights. At this page, output is no longer needed, so we'll use output memory for derivative. We also apply this approach in every other stage. And when apply gradient, we release useless memory too. We apply fine-grained memory scheduling to various layers with understanding memory usage step by step. Through this process, we can achieve a lower peak memory usage compared with other frameworks. Now, let's think about entire model, not just a single layer. When these memory-saving benefits are extended across the entire graph, their impact becomes even greater. We calculate the execution order of the entire graph and efficiently allocate and reuse tensor that can be shared. Through that, we can reducing the overall tensor memory consumption. While backpropagation, other frameworks allocate all tensors and didn't reuse. NNTrainer share memories that isn't needed to be retained between layers and allowing the next layer to reuse it. For example, once the weight are updated, only weight is needed, so other can be shared for the next layer. Through this, we can achieve much larger difference across the entire training process. Example I just shared is quite a simple case. In many real-world scenarios, however, we see much more complex structures like multiple input and outputs, complex weight, shape, or orders in one layer. And NNTrainer handles these complex cases as well, managing each and every component at a highly fine-grained level. Even with the tensor optimization, physical memory is still limited. So we use flash storage with proactive swap. And we call this FSU, flash storage utilization. Using flash storage is not a new idea. However, that approach comes with a major problem. It significantly slows down speed. That's why it hasn't really been adapted in field of deep learning, which, as you know, already time-consuming process. However, we saw an opportunity from computation taking a lot of time. We already know the execution order and which rate and tensor are needed. Then we can load rate asynchronously from flash while the computation is running. That means we can hiding I/O latency. As you can see, while compute layer 2, scheduler will load layer 3's weight. And while computing layer 3, scheduler load rate layer 4's weight. We can also decide how far ahead to preload data using logarithm mechanism, which let us control the amount of memory we allocate. The more memory we use, the more we can minimize the slowdown. We also provide FSU not only for inference, but also for training. FSU on training more complex because right operations. By leveraging the information we already have, we are able to efficiently apply the FSU functionality during the training as well. Thus far, I have explained how NNTrainer was able to reduce memory usage with our key concepts.
All right, so let's circle back to LLM Inference. So so far, we saw that NNTrainer can support memory-efficient features, including tensor optimization and flash storage usage. So you can think that tensor optimization saves memory for tensors, and flash storage utilization can save for memory space for weight. So now we can use these features to run super large language models. So now we are ready to talk about running 30 billion model with NNTrainer. So let's revisit the previous graph. So we want to run more powerful model greater than 10 billion with limited memory. Fortunately, many researchers have addressed the similar challenge in terms of model architecture. And the mixture of experts, also known as MOE architecture, offers an effective alternative. Then what is MOE? MOE refers to a family of large language models where the feed-forward network layer comprises multiple expert subnetworks. Then why is this approach promising? The key advantage lies in its sparse activation. So as you can see, during inference, each MOE layer activates only a subset of experts. This significantly reduces computational overhead while maintaining total model capacity. Also, in practical terms, I mean in terms of memory, although the model contains weights for many experts, but only for a small number are actually utilized during the inference. Then, in terms of actual active parameters, we can redraw this right graph like this. So MOE models would fall within this region, which is below 10B, which aligns perfectly with our on-device AI target. For example, QN330B MOE model has 3 billion active parameters only. And GPT-OSS model has total 20 billion parameters, but its active parameters number is around 2 billion. Okay, then can all MOE models run on device? Unfortunately, no. Significant challenges still remain. So let me explain why. So even when the active parameter count is only 2 to 3B, most standard frameworks and even on-device frameworks require loading the entire weights upfront. This is because the system cannot predict which experts will be needed. But the expert selection changes dynamically according to the input prompt, and it varies for every token. Then how large MOE models should be loaded? As you can see in this table, for full precision models, on-device deployment is entirely impractical. They're over 70 gigabytes. And even quantized versions typically require over 12 gigabytes of memory. This means other frameworks cannot run MOE models even though they have small active parameter. However, NNTrainer can address this challenge through its feature of flash storage utilization we introduced. So these technologies leverages flash storage as an auxiliary memory, enabling a more efficient approach. So rather than loading all weights initially, the NNTrainer can dynamically load only the active parameter from flash storage as needed on the fly. And to this end, NNTrainer currently supports fine-grained level FSU features. Therefore, if you use NNTrainer, you can run 30 billion model with 1.6 gigabyte memory. So when processing 31 tokens, of example here, the peak memory usage drops dramatically from almost 20 gigabyte to just 1.6 gigabyte with reasonable speed. So please note that it was not able to run 30 billion MOE model on device before. Furthermore, if you can use more memory, then you can achieve more speed up. This demo on the left side shows an example of reasoning application on Galaxy S25 Ultra. So this FSU is even effective when memory is sufficient. So this significantly reduces model loading time, which means initialization is much faster. These two videos demonstrate the memory sufficient use cases. So on the left side, we see the conventional approach where all weights are loaded during initialization. In contrast, the right side illustrates loading only essential weights initially and fetching the remaining weights on demand by using flash storage utilization. As you can see, this can much reduce end-to-end response time. Let me show you more examples with powerful models on device. At the beginning of this session, we established our goal, running more powerful models directly on devices. And MOE models demonstrate superior performance compared to smaller models, particularly in instruction following tasks. By running these MOE models on device, developers can more effectively create their own applications throughout simple prompt engineering. These are two simple examples using open weight model with 30 billion and 20 billion MOE models. And we've successfully developed example applications such as English Grammar Assistant and a multilingual common sense reasoning chatbot without any additional training. And also, beyond the memory-efficient features, NNTrainer also tackles efficiency during the actual large language model inference service. Let's look at another feature that boosts overall LLM performance. Nowadays, most of users often build their own personalized assistants using customized system prompts, defining their model's tone, purpose, and rules. Since users want to reuse these, the long system prompt must be fed repeatedly to the model every single time. For example, imagine you want to make an English teacher, and then imagine an English teacher prompt that corrects English diary entries. Then the long teacher prompt on the left has to be processed every time the user writes their own diary contents. And this demands substantial time on a device, slowing down the experience. So to solve this, NNTrainer offers prompt caching as well. This feature stores the system prompt and eliminates redundant processing for repeated inputs. This kind of optimization dramatically improves response times for the end user. So far, we've introduced how NNTrainer can support large language model inference memory efficiently. But NNTrainer is much more than just an LLM runtime. Our framework actually supports both training and inference, and incorporates numerous features for efficient on-device AI development. It also offers extensive flexibility, including the capability for you, the developers, to define custom layers easily. So this is the key if you want to experiment with advanced on-device AI technologies. Also, while today's session focused mainly on CPU implementations, NNTrainer is built to support heterogeneous computing across GPUs and NPUs as well. We strongly encourage you to explore our repository to discover these full capabilities. So here's the conclusion for today's session. We introduced NNTrainer, a lightweight on-device framework that supports not only training, but also highly efficient inference. Crucially, NNTrainer features powerful memory optimization technology, including optimized tensor scheduling and flexible flash storage utilization. This is the key that enables even that massive 30 billion parameter model to run with a footprint of just 1.6 gigabyte. That's a huge breakthrough. Also, we have various examples in our repository showcasing these great features. We invite you to explore those capabilities. So please come visit our repo and join our community. So thank you for listening to today's session. If you have any question, please feel free to come to us. Thank you. Thank you for listening.